I have written down a little bit something I'd like to talk about today. So basically, I'd like to talk about backpropagation. I have kind of I've discussed that before in my class, but I just find that many students have problem with that. So I guess the basic idea is very simple. But let's just give a review what backpropagation first. So backpropagation used in neural network basically. So in general, it can use for any computational graph. It's just a tool to define gradient, or it's a tool to define gradient. And maybe I put a quote unquote for gradient here because I think many misunderstanding is because many of this notation is actually etymology, not precise, even for gradient here. So so what's that for? So just think of a very simple neural network problem. Let's say if I have x here coming in, I have some linear layer. Let's say I have W1 here. I have, let's say, C1 is equal to W1 times X here. Here, this is a linear, this is a vector here, X is a vector, W1 is a matrix, C1 therefore is a vector here. Let's say I have some activation function, maybe a value here. Then let's say I have Y1 here. Maybe then afterward I have, okay, maybe I change the symbol, like maybe I call this Y1. This C1 instead. C1 says after Y1 going for a value layer, then maybe I have another linear layer, let's say W2, and let me call this Y2 here. So Y2 is just like W2 times C1. Or maybe just call for simplicity, just call this Y here. Maybe I have just like two linear layers and I have one value layer in the middle. Maybe this is a regression problem I have some Y tutor is what I want. So, and basically I want to adjust this W1 and W2 such that like this Y is close to some Y tutor here. So I can define some loss function, maybe Y and Y tutor, maybe it's just like some difference between them, maybe some long, square long maybe. Now, as I said, like we want to find the gradient, quote-unquote gradient of this parameter. So for example, like if I know the gradient of W1, then I can go for a steepest descent. Note that what do gradient mean? Gradient just like if W is a vector, so here of course W is a matrix. But in general, if I have not in general, but like for the vector case, I say if I X here, I have some loss here, and the gradient is just the direction of steepest ascent. So we're pointing to that direction plus the gradient Lx is that like for let's say for some x pi here, it's just saying that at location x pi here, there, the gradient is just pointing to the direction of the gradient, just pointing the steepest ascent. It's like going that direction. You go up like most quickly. So if we move along that direction, we'll go uphill with respect to L. So therefore, if we want to go downhill, so we want to have like my x next iteration, x will just change to x, go along the opposite direction of L. So something like typically we multiply by some epsilon, it's like a small step size here. People sometimes call it learning rate and so on. Of course, you can, this is a general, generic, very simple gradient descent optimizer. And of course, you can make it more sophisticated, like include some momentum term so that like it optimizes a little bit better. But in general, like in any of this case, we need to find the gradient anyway. And backpropagation is the tool to find this gradient. So that's what I mean. Like, so for this problem, like if we go back to this problem here, we can have W1 update as this minus some epsilon possible, gradient of W1 with gradient of L with respect to W1 and maybe also W2. So, okay, like now why I say a and co-gradient here is like, typically, okay, when we learn vector calculus, the gradient we are thinking of like is like a one-dimensional object as a vector here, but in this case, this one is actually is a matrix here for this gradient of L and so on. But before we go into this here, let's again look at like what backpropagation helps, or like what is backpropagation help us to find this object here. So let me we use a different kind of like notation for this guy. So instead of using this lapa or like inverted triangle stuff, we'll just write this as parcel L, parcel W1. And parcel L, parcel W1 can be written as parcel Y1, parcel W1, and parcel C1, parcel Y1, parcel Y, parcel C1, parcel L, parcel Y. So I have this is like reported like here, and often like people just say, okay, this is training rule. I have this multiplied by this, multiplied by this, multiplied by this, and that's the problem that like I get. I find that many students have problem with that because when they look at that, they just think, okay, this is some kind of product, or I guess I partially say because some of the terminology, for example, like for gradient, is not explain what I want to say, like as I mentioned, like in fact the calculus we expect this gradient is like just a one-dimensional, or I should say it's just a vector. But here, like oftentimes, because when you go into a neural network, this kind of this partial derivative of this so-called gradient is actually two-dimensional and so on, and maybe even some of them will be like three-dimensional and four-dimensional. So that's why when I guess that's why like students always have the idea, okay, I think this is a matrix, or maybe try to make it a matrix object and then just try to arbitrarily put a transpose here and there, and hopefully they will multiply and so on. And I don't kind of like completely blame them for that, because I think like just the way that this thing is taught have some problem. So so let's look at like just one particular example. Like let me okay, maybe let me see like why students think have this misunderstanding. I guess like where is this misunderstanding is like coming from? So if I have just like a simple one layer case, I have some x and y, maybe I have some f like coming in. I mean f is just apply on this x, or I have a y here. So and maybe this y is related to some loss here. Before we look into this product here, I guess one thing I really like to point out is important is that the partial derivative, let's say partial derivative L with respect to x, let's say x is like a vector with just two to elements like x1 and x2. These things here, this partial derivative, will have the same shape as like x here. So because you think of like what are the elements inside partial L, partial x, it's just like partial L, partial x1, and partial L, partial x2. Right? So therefore, like when the numerator is scalar, numerator L here is scalar, then the partial derivative will just have the same shape as the denominator, as this x here. And this is true for whatever denominator here. So for example, like if I consider W, let's say W have like shape like W11, W12, W21, W22. So the partial derivative L with respect to W, what it means is just this way. Partial L, partial W11, partial L, partial L, partial W12, partial L, partial W21, partial L, partial W22. Again, it's the same dimensional, is the same dimension as W here. This is like very simple, obvious, but at the same time, it's very useful because with that, like, and of course, when we say that, like, when the numerator is scalar, this is true. Then that means that, like, actually, this kind of implies that, like, when it's not, the numerator is not scalar. For example, if I have partial y, partial x, y is not a scalar, then this obviously is not the same shape as x. Actually, if you think of that, like, because like y, for example, is a vector like here, each of them yi here, like partial y1, partial x here, will be same shape as like x here. I have the same shape. Maybe I use a tilde to kind of represent the same shape as x here. So for actually, this actually composed of 3 of this component here, partial y, partial y2, partial x, also same shape as x, right? So I have 3 pieces here, and each of them have same shape as x. Now I can really come to interpret, say, what is this partial L, partial x now. I mean, interpret what is like this product here now. What I can think of is like, when you go for this output here, when the L is trying to pass this gradient information and going for this, I want to see like how it's related to this x here. It go for this y here, right? It go for this y like for multiple, for each elements of y basically. For example, y is like, it's a vector with 3 dimensions, yes, it's a 3-dimensional vector. Then it go for y1, go for y2, and go for y3. So then, like, this product is really like a sum of partial yi, partial x multiplied by partial L, partial yi, and sum over I. So it's like, it can go for each of these element of y. So I can go for y1, and then if I go for y1, then that contribution to the gradient will be like partial L, partial y1 multiplied by partial y1, partial x. And know that, like, for each of these partial y, partial x, we have the same shape of x, right? And also partial L, partial x, we have same shape of x. So the dimension match is very nice. And this guy is partial L, partial y is just scalar, right? So another way to think of that is just my partial L, partial x is just a weighted sum of this partial y, partial x, weighted by like partial L, partial yi. And of course, this sum, like, you can also write it somehow in a matrix form. like this. So if I write it as matrix sum, okay, this is a parcel L, parcel Y, right? This is actually get back to like what we have like earlier. We have a matrix multiplied by this vector, parcel L, parcel Y, and get back like parcel L, parcel X. And of course, like in general, like in higher dimensions, like it's still like this kind of like similar to this kind of weighted sum product. You can kind of probably like put in different way to make it like a tensor product. But this is the key idea. That's what's going on for this product here in the backpropagation step. And I hope that this kind of clarified the things a bit. And maybe we go through one example, just make sure that I explain it clearly. I just make sure that the idea goes through. Okay, let's consider an example that just matches with our earlier example. Let's say I have W coming in, that it's a linear layer. I have Y is equal to W multiplied by X. And let's say X is just a vector here. And then eventually go through some loss here. I got L. Now my then let's say I want to find the partial derivative of L with respect to W. Will be partial derivative of Y with respect to W times partial L partial W. Partial L partial Y, I'm sorry. And again, like this times, we should be very careful. It's really meaning this kind of product here. So it's a weighted sum, so therefore it's like something like partial Y I partial W times weighted by partial L partial Y I over I. Here. In my again, like because Y I here is scalar, so the partial Y I partial W actually have same shape as W. And also partial L partial W same shape as W. And the scalar, so everything matches pretty well. The dimension matches pretty well. And now then the only thing maybe we should try to find is partial Y I partial W here. And we know that first of all, maybe like what is YI first? YI is just equal to WI 1 times X1 plus WI2 times X2 and so on and so forth, right? So now if I have a partial YI partial W, maybe I look at the LM element of that will be equal to partial Y I partial WLM, right? So what you see is like, if L is equal to I, then along this sum here, there will be one term here. Like I will have a WLM somewhere, but WLM will be multiplying with XM there. So therefore, this will be equal to just XM when L is equal to I. However, if L is not equal to I, then there's no such term exists, right? So it'll be just equal to 0 otherwise. So it'll be something like that. Then that means that like the LM terms of this guy is equal to just XM here. That means that like partial YI partial W will be just equal to have all the rows basically, have all the rows is equal to 0 except for the I row. Let me erase this line here. Except for the I rows, that will be just equal to X, or like X1, X something. So this basically have an X transpose here for the I row. Something like that. So then if you look at this weighted sum, that's actually we'll have partial L, partial Y, partial W be, let's say like some one, maybe I just write this summation into like partial Y1, partial W, partial L, partial Y1, plus partial Y2, partial W, partial L, partial Y2, and so on and so forth. Now let's look at the first term. That partial Y1, partial W just means that like I have a first row here is X, transpose the rest is like 0, and multiplied by partial L, partial X, Y1, right? So I have partial L, partial Y1 here, and all 0 rest afterward. And for the second sum here, it would be like the first row will be 0. I mean, for partial Y to partial W, first row is 0. Then the second row is X transpose, and the rest is equal to 0, and multiplied by partial L, partial Y2, and so on and so forth. You see the pattern is like basically just equal to partial L, partial Y1, X transpose, partial L, partial Y2, X transpose, and so on and so forth. So therefore, eventually it's just equal to partial L, partial Y1, partial L, partial, it's hard to write. I guess I can erase this in here now. So it's equal to partial L, partial Y1, partial L, partial Y2, and so on and so forth, times X transpose. So this is like partial L, partial Y. And of course, if you look at this here, like this is partial L, partial Y here, and this is partial Y, partial W. And of course, like if we start looking at this at the beginning, partial Y, partial W, oh, okay, of course it's equal to X. It's just calculus. But then I guess it's missing the point. Like this is like it's not a scalar case. Of course, like this is good to just for verification. So for sanity check, when we are done, then like we expect like if this cup degenerate to scalar case, partial Y, partial X is just partial Y, partial W should just get me X. So in this, if I go to scalar case, X transpose is just equal to X, so therefore it matches. But you see that we cannot write at the beginning saying that, okay, this should be just equal to X or X transpose. This is like, I see like this is the mistakes like students always have. So anyway, I guess I probably just stop here. Hopefully like it makes things a little bit clear. I guess the main idea is here, like whenever we have this backpropagation step, like this product of two partial derivative here, this product like need to take extra attention. It's not really a scalar product, not even a matrix product. Like sometimes, I'm actually most of the time it won't be. Only in the case when this guy, I mean the input and output vector or like scalar, then you will have like those nice cases. Otherwise, if like your input and matrices or like even more higher dimensional objects, then this product like will be like some, I assume it's a complicated matrix tensor product, but I mean like really like it won't be like a product you can write it in a very very much like simple form, or like just a write it in a very what's that word, concise way. So but it's not bad at all. One want to say it's not bad at all. Like if you think of that, like what's going on is just like because you're going for y have many elements here, right? So this is just saying that like we should go for each of the element of y. So therefore, like for going for each of element of y, this partial derivative of yi with respect to w should have the same shape as W. So we just weight the sum by the gradient that coming back, like weighted by the each element of the corresponding element of the gradient that coming back. So therefore, it makes sense. Everything makes sense. Just need to be more careful with the detail. So okay, I really will stop here now.